So I have to admit that has been one of the most tough presentations to prepare in my life, to prepare such a experimental talk on radiation in a meeting of theoreticians on completely different topics. So also because I wanted to make it not too silly and neither too technical. So let's see the outcome.
Mi piace che adesso un anno molto creativo.
Ah, bene, ottimo. Yes.
He's looking forward.
Yes. It's advancement. No? It's really advancing.
That's the future of experiments. So.
Okay, so let's see the outcome. So here you see the very usual picture of how the radiation are are divided, classified, yes. And let me start with just a curiosity, because here you see that you have an overlapping here. We are used to define soft X-rays, hard X-rays, gamma rays. So at some point here you have a mixture. And okay, the solution here is that usually when you speak about gamma rays, you are dealing with something coming from nuclear decays or something like that. But here you want to keep some nomenclature for X-rays, because X-rays are usually the ones which come from atomic transition, but there are some elements in which these energies are so high that they start to mix with the gamma rays. So this was just a curiosity. In this talk, I will try to speak about some detectors starting from, let's say, few electron volt up to the end, basically. Of course, I'm not here to speak about all the possible detectors that exist in the world. I will just mention a few of them, basically the one we are working with, and also I will try to tell you what do we use this detector for. In particular, I will try to speak briefly about microcalorimetry, so transition at sensor detectors, Bragg spectrometers, and then silicon, cadmium, zinc telluride, and germanium detectors that, as you know, are semiconductors. Then let's say that also it's nice to see what we want or could measure with such detectors. Of course, we can measure energy, and this will cover mostly 90% of the talk. Then we can measure position, and we can measure also the multiplicity, so the number of photons that you are obtaining. In principle, you can also measure direction, time, and rates. But for a reasoning of time, this will not be covered in this talk, except one sentence about direction. And then how? Then here, when I was preparing these slides, I thought that maybe also for you, a few times in a lifetime, it's nice to see, or at least to refresh your memory on how, in particular, semiconductor devices work. So which is the physics principle beyond them, and okay, some very basic concept. And of course, when you speak about detection of photons, you have to speak about absorption. And it's important to remember that photon absorption is basically a binary process. You don't have energy loss like for charged particle, but you can have the photon is either absorbed or not absorbed, basically. And here you see the three main processes thanks to which a photon can be absorbed. This is a plot in which you see the Z of the material, and here the energy of the photon. And you see the three very distinct regions in which these are the dominant processes. The first one here is the photoelectric effect. This is the main effect for visible X and gamma radiation. This is exactly what you want to maximize usually in the most part of the detectors. And here it's just important to notice that this is proportional to this power of Z. So of course, this has an implication when you decide which material you want to use. Then you have Compton scattering, which usually you want to completely avoid, because Compton scattering gives you something which is not directly proportional to energy. You have a broad distribution, so usually it's difficult to have it and you want to avoid. And also you can have pair generation, which is the main effect for really high energy physics, and it's not interesting here for the range we are covering here in this talk. So let's start with energy, and as I told you, this will be most of the talk. And let's start with semiconductors. So here you see a very naive picture of what do we mean by semiconductors. So you know that in whatever material you have a conduction band and a valence band. And this is how these bands look for insulators. So when you have a very huge gap between these two bands, semiconductor here, and conductor when these two bands are overlapping. And in the mid, you see the so-called Fermi level. So what is Fermi level? There is a function which is called Fermi distribution, actually, which gives you the probability that a given available electron energy state will be occupied at some energy. Here, just to put some number, that this constant here is 0.025 electron volt at room temperature. And this means that actually, if you have something in principle at absolute 0 Kelvin, this means that you cannot have one single electron which is available to be promoted in the conduction band. But then you can start to play a bit with the temperature, and your function becomes like that. So you can start to have some electrons which are available for P to be promoted in the conduction band. And as you will see later, this is the, of course, important issue to have when you want to use semiconductor detectors. So the message here is that playing with the temperature allows moving the Fermi level, which is the energy you see here, and which corresponds in principle to something in between the two bands. Why the Fermi level is so important, you will see in the next slides. Here is just a recoil on the main elements which are used as for semiconductor devices. And you see here that these elements have a band gap which is decreasing with respect to the, let's say, the dimension of the lattice of these elements. You start with carbon, diamond, basically, this is a complete insulator, and then you can start moving. And if you put this number here inside this formula, this gives you the probability that you have a thermally promoted electron. So basically, this is your background. And this explains how, I don't want really to go into detail, but this is the motivation why some of these devices need to be cooled down. Because in silicon and most of all in germanium, you need to cool down the detectors in order to dramatically reduce the probability that you have some electron which is promoted unwantedly. And so this ruins your signal. Then this is a slide that was used to show in some classes somehow, but okay, I like it, so I will put it here again. Physicist. Yeah, this was really old one.
Also physician.
You're right.
Also physician. Since our life.
Your life. Sorry.
Maybe it's much more important.
Actually, I recovered these slides, which is really old. Maybe I was still studying English.
I'm teaching to people from the medicine school here, and I must say that, like, anything else.
So anyway, let's imagine that you have some scooters in front of a red traffic light, and at some point the traffic light becomes green, and then okay, the first one starts to move, then the second one also is moving, and so on and so forth. And then you want to describe this. So here you can either, I don't know, write the motion equation for each of these, and okay, these are a lot of equations actually, or you can do something simpler, which is describe the motion of this single hole here. And this is exactly what is done in the semiconductor physics. So we describe the world also in terms of holes when it's convenient to do so. So in principle, you have also the possibility to introduce some further levels here, doping these materials. Also here, really, I don't want to go too much into details, but the idea is that playing a bit with the bondings of semiconductor with some other elements, you can create some new levels here, which are much closer to the conduction band, so you can more easily produce and promote electrons in the conduction band, or the opposite for the holes down here. And then what is happening is that at some point you want to have one of these, and put them together. When you put them together, so you create a so-called junction, then you have something which is really important. You have that, of course, in this region here where you have more electrons, here you have more holes. And then you have that your electrons, of course, wants to go through the junction to fill the holes. But then when they are moving here, somehow they left some negative ions on one side, and here they create some positive, create some negative ions here and left some positive ions here. And at some point you reach an equilibrium in which you cannot have any more this flow because the equilibrium situation is reached. And so at the end, the final conduction and valence band of your junction looks like that. You have the Fermi level. Now here's what this Fermi level was important. They align together, the two Fermi level of the two materials. And this is the situation. This means that now if you apply a voltage which is negative here and positive here, somehow you even impede the flow of the electron again, and so you create a barrier. While in the opposite case, you favor the passage of the electron near the to the junction. And this is exactly what happens with the so-called diode. This is the very basic principle of all semiconductor detectors. So if you have this junction, you put a voltage. If you do it in the right way, you have some electric flow. So you have some current flowing. And in the other case, in principle, you don't have, as you will see maybe in the last slides if I will have time. In some devices, if you really put a very big reverse bias, then you can have other effects, and you can also have some currents. But let's focus on here. And this so-called PN junction is the elemental brick for all semiconductor devices that you will ever find. So close this parenthesis of basic principle of how this works. Let me just go to show you some of the detectors that we are using in our lab, but not only. And let's start with the silicon drift detectors. As you see here, again, the basic is P+, PN junctions, again, with some ad hoc geometry. And the idea here is that if you have some particle, which, in this case, photons, which arrives here, then you have photoelectric effects, and then you create these electron-hole pairs. And then the first thing you want to avoid is that this electron and hole recombine themselves, so you lose your signal. But in this case, what happens here is that you have so many, let's say, rings of the P+ type, that the holes which are created here are immediately captured by these stripes here, and then the electrons are really free now to move towards the anode center, and this in favor the quality of your signal somehow. For each type of detector, I will also try to give you some pros and cons, so the main idea is that if you want to make some experiments, then you looking at these slides may at least say, okay, maybe this could be nice for me. I could use this detector or this other one. So the very good feature of silicon drift detector is that these are completely linear. You can see here that you have all these elements which have been measured with here with these devices, and you see that they are very completely linear in the energy calibration. They can be built with very large area, so you can build very huge detectors, huge square centimeter of detectors without many problems. And these are very fast, and at least for us, in our case, when we study Colonic Atoms, this is a very important situation. I will tell you in the next slide. This is not a pro or con, this is just a fact. They are suitable basically for a very small range of kV, from 4 to 20 kV. And the resolution is limited to 100 electron volt, more or less. This is just physics, it's due to a so-called Fano factor. You cannot reach resolutions below this value. What do we use this for? I don't know, maybe some of you already heard about Colonic Atoms. I would just one slide here to show you again what we do. So the idea is that you imagine you have an hydrogen atom, for example, in which you have the proton and the electron. Then you can have a K- which arrives, kick out the electron and takes its place. Then, if you just put the numbers in this very naive formula, you see that once the K- arrives here in the position of the electron, now for the K-, this distance to the nucleus corresponds to something like n equal 20. And of course, this is not the ground state for a Colonic atom. So the kern starts to decay towards the innermost levels, which are, in this case, the last ones are 3p, 2p, and 1s. So you have the K- is coming down and it reaches, for example, the fundamental level. And then, since the K- is not an elementary particle, you have quark inside. So now this is so close to the nucleus that it starts to feel the effect of strong interaction. So you can easily, not me, but theoreticians can easily calculate the purely electromagnetic values of these levels. So you can know exactly the transition, so the X-rays that should be emitted from the transition between some of these levels. And if you see a deviations from these pure electromagnetic calculated values in terms of shifting in energy or broadening of the line, then from these ones you can obtain information about the effect of the strong interaction. In this process, there is also a very important issue to be taken into account, which is the atomic cascade, and this will be addressed by Simone this afternoon, so follow his talk later. And so, what do we do with silicon drift detectors to measure these kind of atoms? So we have in Daphne, actually, we have the production of K- at some point, and you have K- entering. We let them enter in a gaseous target. For example, in this case, it was hydrogen. You slow them down before. Here you form these conic atoms I showed you before, and then you look for X-ray transition to the lowest level. And so we put not one silicon drift detector, but hundreds of them around this target cell, and we measure the spectrum of the emitted energy. This is one of the most important results we obtained in 2009. So the most precise ever measurement of the 1s level shift and width of conic hydrogen. This is just the spectrum that we published, and these are the results that we obtained. And as you see, we have some error in the order of some tens of electron volts, which of course is also due to statistics and to the fact that we are using this kind of detectors, which for this spectra here are probably the most suitable detectors you can have. And also I mentioned at the beginning that it was important for us that these detectors were fast, because of course in an accelerator you are completely overwhelmed by background. You want to avoid this background. So we use two plastic scintillators in order to identify K- via time of flight and to trigger these X-ray detectors with the passage of K-. So if your detector is not fast enough, you cannot do this operation, which for us was fundamental. Then, since this is a talk in principle also in advancement radiation detector, then it's also nice to notice that, for example, the measurement of the same level shift, so 1s in conic helium, is one of the most wanted measurements in our community. But this transition is expected at 30 kV, more or less, which is out of the range of silicon drift detector, at least the one that we used until now. And this is why, in principle, you would like to use thicker SDDs. But unfortunately, it's not just so trivial. You cannot say, okay, let's use thicker silicon layers. So there are some technological issues that you have to solve. And this is what we also started to do it in collaboration with the FBK and Polytechnic of Milan. And already we have some prototypes of detectors of 800 micron thickness and 1 millimeter thick. And the outcome is really nice. You see that at 60 kV, which is completely out for our range of normal SDD, you enhance your signal of a Lichter factor 2. This is ongoing. We have already some financement by INFL. So this is really an advancement that we will see in the near future. Then another semiconductor detector which is really interesting is cadmium zinc telluride. In this case, the pros are a very high efficiency and linearity in a broad energy range. You can optimize them between 20 kV and 2 MeV in principle, depending on thickness and some parameters. And in all these range, they have very good energy resolutions. And most of all, they don't need to be cooled because the gap of the cadmium zinc telluride is such that you don't need to cool them down in order to avoid background. And these are also very fast and so they are suitable for triggering. The only disadvantage is that this is a very recent technology, at least at this level, and it's not commercial. You cannot just go and buy a new cadmium zinc telluride exactly for what you want. So you have to somehow produce it ad hoc. This is just a picture of one prototype we measured in Daphne. This is how a typical spectrum of, for example, an americium source would look like. And here it was just to show that you have a resolution of about 6%, for example, at 6 kV, which goes down at 2% at 500 kV. And this is a really nice result if you look at some numbers, because what we were showing here is that the linearity, so the calibration that you use here stands also at 511 kV. This means that the linearity is really well preserved in a wide range of energies. And that was important for us. We also did already some tests in Daphne because nobody until now put some kind of detectors in an accelerator environment. So we were concerned about possible radiation damage issues or something. And so we wanted to have a look at this. we installed one prototype here, very near to the Daphne interaction point, where now we have the Siddhartha experiment ongoing. And we have so promising results in principle on beam that we already have a first technical paper which has been submitted. And the results was, as I showed you before, that the linearity is preserved also on beam, and then that the background can be reduced into the trigger. Also here, I don't want to go too much into details, but that was the outcome. What could we use these detectors for in the future? Well, if you look here, you have just, for example, a portion of the table of the present most updated database on Colonic Atoms that you can find in literature, which dates back to '94, by the way. And you see here that some of these transitions have really huge errors. Some of them are completely incompatible. So we had a lot of discussion with theoreticians, and it was very clear to us that this database needs to be renewed somehow. And this could be done in principle with cadmiums in telluride, because they are able to cover this very wide range, and they don't need very special cooling or something like that. The idea could be to have, for example, to put a scintillator very close to the beam pipe reductor where you create K-, and then you have a degrader and then a target where you create solid targets, in this case, where you create atomic conic atoms, and then some cadmium in telluride detectors to detect the X-rays which are emitted. This is a very simple setup which could be realized actually, and we already started to investigate and to make some Monte Carlo simulations for that. So this is also something advancement which is in principle arriving in a short time. And the third one is the high purity germanium detectors. You also have seen something related with the RIP experiment in these days. The most important advantage of these detectors is the extremely high resolutions also that they have in this wide energy range. But in this case, as you know, they need cryogenic cooling, so you need to cool them down to very low temperature. And also with this, well, they are more subject, let's say, to radiation damage with respect to cadmium zinc telluride, for example. This is how a typical germanium detector looks like. As I said again, PN junction, very naive PN junction. The problem here is that in principle, if you use these kind of detectors, which are called planar, so you just have a junction, the maximum region in which you create this depletion, so where you don't have any more this flow of electron and holes, can be just 1 to 2 centimeters. And since this is exactly the region where you want to measure your signal, then you need to find a solution, because if you want to go to some MEV photons, you need at least 5 centimeters. So this is why now they build this so-called coaxial germanium detector. So if you heard this name, just remember that this is the geometry in which, but instead of having just this geometry here, you have that the N plus contact is surrounding here. So basically you are depleting here, here, and here. And with these detectors, you can reach a very nice resolution. You see this an example of one spectrum. And these were the resolution that were obtained with the prototype that we are using now, built in Zagreb by our colleagues from the University of Zagreb. What do we want to use them for? The idea is that germanium detector can be used also in Daphne to perform a new precise measurement of the K- mass. How do we do this? Again, we have the germanium detector near the beam pipe. You have a scintillator that you want to use as a trigger. And then you create here in a LED target, for example, Colonic Atoms, and you measure them with germanium detector. In principle, if you with very simple calculation, at least at the first order of magnitude, you can see that with measuring the transition of this transition of Colonic LED, we could be able to pin down the error on the count mass at the order of 5 keV. Nowadays, the error is in the order of 11 keV. But the most important problem here is that nowadays the measurement of the count mass is still puzzling, because basically the two most recent and most precise experiments that are used to provide this number are not compatible among themselves, and this increase a lot the error. So it's very important to have this also, because the count mass impacts in other fields of physics, like for example the physics of D-meson also. And so this is why it would be important to also perform these measurements. So this is now closing the part of semiconductor detectors. And let me go briefly to Bragg spectrometers, which are completely different technology and completely different type of detectors. So as you probably know, Bragg spectroscopy means that you have a crystal in which has a typical lattice parameter. And then you have a source of X-rays, which are emitted. They impinge on the crystals. And if they match the so-called Bragg law, they can be reflected here. This means that photons arriving with the same direction, but different energies are reflected in different positions. So if you have a crystal and a position detector, then you can basically obtain an energy spectrum with very, very high resolution just from the position detector here. And this was the sentence I was mentioning at the beginning, just one sentence. In principle, if you know that you have a photon which is monochromatic, you can also test the direction from which the photon is coming from, because if you don't match the exact direction, this is not reflected. In our cases, we tried to also to have a geometrical configuration and a type of crystal which is called mosaic crystals to improve the collection efficiency, because of course if you want to have a direction you need to have a source which is very small, in principle point-like, and so this dramatically reduced your efficiency, so we want at least to raise it up a bit. And you see here a sketch in which we have a cylindrical crystal and how different energy photons are reflected. So you see here that if you measure the arrival position of the photon, basically you obtain an energy spectrum. The advantages of this kind of technology is that you can have extremely low resolution, high resolution, so full with a maximum of few electron volts without cooling. Also in this case, you don't need to cool the crystals down actually. The fact is that the energy range typical of Bragg spectrometers is between 1 and 20 keV. This depends on the crystal and of the order or diffraction which you want to use. And what is below is coming here, you don't see it because you have this cover, but what is written here that you have an extremely low geometrical efficiency. This is the really important issue that one wants to avoid. And this is what we tried to do in Frascati with this project here in 2016, 2018, but this is still going on actually. So we tried to see if we were able to find a geometry in which you can maximize the source, so you don't have any more a point-like source, but you want to enlarge it at least to the millimeter level or centimetric levels. Of course, this is including some background, because if you have a wide source, then you can have photons which are starting from different position, but all having the right direction, the right energy. So when they are reflected, they arrive at different position, but they are photons of the same energy. So you broaden a bit your resolution. And this is how our final setup was looking, or still looks like in our laboratory. And this is what we obtained. So you see that we obtained very, very nice spectra. This is copper, zinc, and nickel. If you look at the numbers here, you see that you have resolution of few electron volts, really nice. Really, really nice. Imagine that with a silicon drift detector, this would look something like this. And also, what was important for us was to show that this was obtained with some sources already in the order of few millimeters. That was important. Okay, this is just a table of the summary of the most important results we obtained. And what do we use this for? Also, not only we are not only speaking about conic atoms, we are also trying to have some nice application. So we actually use this setup also in these other two projects, which were aiming to measure the quality of wine. So this was nice to be done at some point. And so the idea is that in principle, the beta line of iron can be a bit shifted or at least change in line shape if this iron stays in different oxidation states. And the idea is that when the wine gets oxidated, the iron which is contained in the wine also changes the oxidation states. And if you manage to have a look and to catch the difference between the line shape of your iron in the wine, you could be able to understand if the wine is oxygenated or not, or at least if this is a bit deteriorated. And this, we just started to do it now. At the beginning, we used a medical. So this is why physicians, you see, we use a medicine at the beginning, because this is basically iron 3. So we use this to have a signal of iron 3 with respect to normal metallic iron. And we started to see some difference, but okay, this is just the beginning. We have to work a bit on this. And of course, we don't forget our origins. So we still want to measure Colonic atoms in principle. And with this kind of detectors, you can do it with solid targets like this. For example, you can just put your spectrometer on one side and you have a solid target here, and then you see the X-rays which are coming from the Colonic atoms, which is produced there. Or you can even imagine to have a gaseous target surrounding the beam pipe, and where you can put several arms of spectrometers to measure several lights. Then, I don't know, time more or less, then, okay, just briefly, let me mention that there is also another opportunity to perform extremely high precision measurements of X-rays, which are transition edge sensor. The working principle is completely different with respect to the ones I've shown you before. Here, the idea is that you have a material which is brought down below the critical temperature, so it's in the superconductive phase. And then you have an absorber. And if you have an X-rays which arrives here, somehow the absorption of these photons is creating an increasing temperature, which somehow leads the material to the normal conductive state. So you have a sudden flow of current. And somehow this delta T that you can measure is proportional to the energy of the photon which arrives here. And thanks to this, you can reach precision, which are in the order of, also in this case, resolution of the order of 2 electron volts. Exactly like for the crystal spectrometers. The geometrical efficiency is a bit better than the case of crystals. You don't need a very point-like source, but still now they have very small surfaces, so you need a lot of them if you want to cover a very wide solid angle. But this is a problem because at least now they have extremely high costs. They are non-trivial to be calibrated, and most of all, they need to be cooled down to temperature in the range of the millikelvin regime. So you need this very difficult technique to cool them down. There are cooling cycles for days, so it's really not so easy to handle the test. So you don't just know, buy one test, you put it in your lab and you use it. So, okay. And these are two typical spectra that you can find in the literature obtained with such kind of detectors here. What do we use them for? Again, Colonic atoms. Also, this was measured by our colleagues in our collaboration with the Japanese people at JPARC, where they measured the Colonic helium transition to the 2p level with an incredibly low precision, below 1 electron volt. Here you can see the results. And this was very important, very nice results. It was published also on PRL. Now let me briefly go to, as I said, position and multiplicity. Position detector, in particular for us, are useful in the sense that we are using them with the Bragg spectrometers, because I told you that we need position detector. And how are position detector made? Basically, you have strips. So you can have a strip of PN junction. And so this gives you very basically the position where the X-rays is arriving. If these are small enough, then you have enough resolution to really see a track. And if you want to have a two-dimension geometry of the arrival position of your photon, then you can have either double-sided strip, or even better, the so-called CCD. This maybe you heard a lot about that. You have pixel detectors, which the photons arrive, they are measured, and then you read them and you obtain a map of the arrival position of your detectors. Concerning multiplicity, one detector that we used, I used at the very beginning of my career, let's say, they were the so-called multi-pixel photon counters. This works in completely different regime. Here we are speaking about visible photons. And these are very nice. This is a matrix of pixels. And when you have a photons which arrives, one single pixel is hit, and this gives you one signal. Then you go again with another one signal, another, and another one. And so somehow, thanks to this, then the outcome of the whole detector is exactly the sum of these signals, which means that you have a final spectrum in which you can really count the number of photons which arrived on your detector. This can be used for experiments which you need to know the number, a low number. You want to measure a low number of photons, and you want to measure the multiplicity, for example. Actually, the quantization of the signal is even visible on the oscilloscope. You see, this is the signal 1. photon, 2 photons, 3 photons. And this is just a naive curiosity. I use this for students to let them measure, for example, from here, if you integrate this curve here, you have the charge which is collected, and from here you can basically calculate and estimate the electron charge. This was nice for the students, actually. These detectors are really nice because they don't need to be cooled down. They work at room temperature. They are completely safe from radiation damage. They can work in magnetic fields. Some facts are that you can only measure a few photons, otherwise at some point you start to saturate them. They work only in the visible photon range. I heard that there are some attempts to directly measure X-rays with them. So heating X-rays directly on the pixels, but with this we don't do it. And of course you have some unwanted effects, in particular saturation. So you see at some point when the number of photons becomes too large, you can increase the probability that more than one photon arrive on the same pixel, and then you lose this linearity. So this is basically leading me to the conclusion. The two main messages I want to convey here is that the radiation detection methodology is evolving very fast, and now we have the possibility to perform new experiments, which became feasible now with thanks to these new technologies. And most of all, the triggers for new experiments on fundamental physics are very welcome, in particular from this audience here, which is very suitable for this kind of experiments. Thanks.